On Titan, a dark storm gathers above a sea. Methane falls as rain, and it cuts rivers through water ice before disappearing beyond the horizon. But sunlight destroys the methane feeding this weather, so without a hidden supply, it should have died long ago. This is Cosmion. Point it at any question in the universe, and it will show you the answer, whether you can bear it or not. Tonight, we follow one imagined drop from a northern cloud to the sea, then ask, what keeps replacing the methane above it? No telescope tracked this drop, so it becomes our guide through observations of one working climate without pretending one camera saw the entire journey. So our trail begins in July 2023, when Webb watched a cloud standing above Titan's northern lakes through the orange haze. Then, 3 days later, Keck saw the cloud higher in the atmosphere, which told us methane-rich air was climbing through Titan's weather layer. Even so, no camera saw rain fall beneath it. And that evidence limit changes what the film can show, because direct images end when we leave the cloud. From there, a labeled reconstruction has to carry the measured physics. From there, the reconstruction follows methane vapor rising from the northern seas as the air carries it into the waiting cloud. As it cools, molecules gather into droplets, much as water does inside an earth cloud, except this liquid can burn in air. Eventually, one droplet grows heavy enough to fall, and the storm releases it into a sky almost 600 kilometers above the ground. From that moment, it follows a journey no real drop has survived long enough for us to track. So the route remains openly imagined, with real measurements deciding what the reconstruction can and cannot show. To begin with, Titan's lower air is mostly nitrogen, while methane makes up only 1 part in 20 around our falling drop. And near the ground, that air presses 60% harder than Earth's, which feels like water 15 meters above a diver facing the surface. So our drop is falling through weather with real weight, powerful drag and almost crushing depth, rather than some thin alien mist. Above the falling drop, the cloud tower can rise through a troposphere nearly 45 kilometers tall, almost 4 times Earth's weather layer, while below it waits a world at minus 179 degrees Celsius, colder than any natural place measured on Earth's surface. In that cold, the frozen water beneath the storm is no soft snow or flowing glacier. It is bedrock. Yet methane can still move through 3 familiar stages: gas in the sky, liquid in falling rain, and liquid pooled across the frozen ground. And then the drop strikes the ground on the only solid world besides Earth known to receive rain beneath an active weather cycle. But this is no summer pavement. Instead, the ground is hard water ice, stained by carbon-rich dust that has drifted slowly from the thick orange haze above. From there, the liquid gathers in shallow grooves and joins other drops before following storm water's path down an earth hillside. As more rain joins it, a groove becomes a channel, and it cuts deeper whenever the sky sends a flood down the same slope. And this is where the missions help. Cassini mapped branching channels through the haze, while Huygens showed the frozen ground beneath Titan's orange sky. Neither followed our river, but together they revealed the world it must cross. So that gives the reconstruction its physical chain. The sky rains, the surface drains, and the frozen landscape keeps the marks of each passing storm. By now, our drop has joined a stream too shallow to name, then another, until water ice banks steer a methane river north. And from this height, Titan starts to look organized, with a complete weather system moving liquid across a frozen world. But this river carries liquid natural gas rather than water into the darkness gathered around Titan's northern pole. Before the channel widens, the current slows, and our single drop passes beyond the river mouth into a wide body of open liquid. And ahead lies Ligeia Mare, one of the great northern seas Cassini's radar revealed through the haze. And although we have measured its coastline, no human eye has stood beside that dark water. And most of Titan's lakes and seas crowd into the north, where summers can feed methane weather for many Earth years at once. Because a single season lasts more than 7 Earth years, Titan's weather moves through a calendar far longer than a human one. So clouds can grow over the same northern reservoirs that feed them, sending liquid inland before rivers slowly bring part of it back. Taken together, the mapped northern liquids cover an area close to North America's Great Lakes, although the chemicals inside them are completely different. So that comparison gives us the scale. Even though the coast would feel nothing like Earth's, almost everything would be wrong. Instead of trees, gulls, and salt spray, there is a shore of frozen water beside a dark sea of methane mixed with liquid ethane, and then our drop enters without a sound we can hear, becoming part of a dark reservoir large enough to influence the weather above. The imagined journey has to end because there is no honest way to identify our drop among countless others in the sea. So the sea takes over. As the camera pulls back, Ligeia Mare spreads beneath the storm like a piece of endless night, cut into Titan's pale and frozen north, far below the cloud. Cassini often found an extremely smooth surface, which left researchers asking whether Titan's gentle winds can roughen these seas, because the calm might mean weak winds, quiet weather, or Cassini arriving between rare storms. So in 2026, a study tested that question with a computer model called Planet Waves, built specifically to make waves on alien seas. That model covered Ligeia Mare in the north and Ontario Lacus in the south, calculating how seasonal winds push energy into the liquid. But this is not footage. Instead, it is a prediction combining Titan's gravity, dense air, liquid properties, mapped coastlines, and expected seasonal winds. If one input changes, the modeled waves change in height, speed, or direction. On ordinary days, the winds almost never cross the threshold needed to make waves, so the broad surface remains close to perfectly flat. But when average storm winds reach about 1.5 meters per second, the model raises waves between 15 and 48 centimeters. Even then, the waves reach roughly ankle to knee height, driven by a wind gentle enough to barely trouble an ordinary flag on Earth. And in the rarest modeled storms, winds near 4 meters per second can build broad waves roughly 3 meters high above the dark surface. Those waves rise slowly, with as much as 32 seconds between crests, turning the quiet hydrocarbon sea into a vast moving wall. It is a dramatic image, but the limit matters more. Cassini never filmed those waves rising, and direct evidence of waves on Titan remains rare and difficult to confirm. And that is because maximum winds may arrive 2 or 3 times in a Titan decade, while ordinary days leave the sea almost flat. Even with the same wind, Titan can raise a much larger wave than Earth, because its gravity is weaker, its liquid lighter, and its air denser. Then, as the storm passes, the modeled waves lengthen and lose their force, and Ligeia Mare settles back into the darkness around it. And that is where the story turns from movement to cost, because every cloud, river, and wave spends methane from Titan's limited atmosphere. The cycle looks circular from below, yet chemistry opens a leak high above the weather. That leak opens because high above the sea, sunlight breaks methane molecules apart before the weather cycle can return every piece to the sky. And from there, some fragments become ethane and heavier compounds before sinking towards the ground, while lighter pieces, including hydrogen, escape into space. More recently, Webb caught a short-lived fragment called methyl, which gave scientists direct evidence of methane destruction across Titan's atmosphere. That places methyl between the original methane and the heavier products that follow. So the storm carries a hidden bill. Every cycle returns liquid, but upper atmosphere chemistry does not return all the methane that the weather spends. Over enough time, the atmosphere should lose its methane, the clouds should thin, and the dark rivers should stop reaching the northern seas. Even then, Titan itself would remain, but the world we recognize here would become quieter, drier, and darker, beneath a slowly changing sky. Even without an exact clock, the problem is clear because sunlight is still working high above, while Titan's methane weather remains active far below, which means something must be adding methane, or Titan's atmosphere would have spent this supply and lost the active weather we still see. But that opens a deeper question. What is supplying all this methane? We know the input must exist, although nobody has caught its root in action. For example, one idea is cryovolcanism, where cold material rises from inside an icy world, replacing Earth's glowing lava with water, ice, and gas. In that picture, a vent might release methane trapped below, while methane-rich material moves slowly through deep fractures in Titan's frozen outer crust. But even so, no confirmed methane volcano closes the case. Below that sits a salty water ocean, 55 to 80 kilometers down. Yet the ocean is not automatically the source of atmospheric methane, so the deep ocean, cracked crust, and active sky can all exist together without proving that methane moves between those separate layers. What scientists know is that methane must be replaced if the cycle has lasted, but they still do not know what keeps paying the atmospheric bill. So that leaves us with branches, not one glowing pipe. Methane might rise from below, wait in the crust, or use a hidden route. And far above that uncertainty, the northern air keeps moving as another methane cloud begins to climb over the same map seas, even though the atmosphere does not wait for scientists to solve the machinery beneath its surface. For now, Webb can watch the cloud rise, and a future mission may test the ground directly. But today, the connection between sky and interior remains hidden. Meanwhile, our imagined drop is gone inside Ligeia Mare, even as the cycle that carried it prepares another high above the frozen coast. From the sea, methane rises, cools in the towering sky, and gathers into a new weight above the pale shoreline. And for a moment, the whole case returns to one simple image: a dark cloud holding cold rain above a silent, frozen world. So the real mystery is repetition. Sunlight keeps destroying the fuel, yet somehow Titan is still raining. If you want to follow the next investigation when it lands, subscribe once and come back. Cosmian publishes one a week.